Welcome to this explainer. Today, we're doing something really cool. We're peeling back the complex layers of modern search engines to see exactly how computers understand semantics and execute massive queries at absolute lightning speed. You know, if you've ever wondered how the search bar on your favorite e-commerce site seems to literally read your mind, well, you are in the right place. So take a look at these two phrases. A traditional legacy exact match search engine completely fails to connect them, mostly because it's only looking for the literal characters RED. It doesn't inherently know that crimson and red are the exact same concept. And this limitation perfectly sets up our journey today into semantic discovery, where we're going to teach systems to search by meaning rather than just by spelling. Okay, here is our roadmap for today. We'll be covering the cost of search, words as math, measuring similarity, navigating space, Qdrant's one-bit compression, and finally, fast execution. Section 1. The cost of search. Before we even touch the math, we really have to look at the architectural baseline. High-scale engineering teams are actually moving away from traditional fully managed search-as-a-service platforms like Algolia, and it's all because of this financial reality. When your platform has low traffic, a managed service is incredibly cost-effective. But consider what happens at a high scale, say 15 million queries a month, which is surprisingly easy to hit when you have instant search as you type keystrokes. At that scale, an open-source pipeline using change data capture, Redpanda, Typesense, and Qdrant saves over $400,000 in its first year compared to a SaaS solution. That is a massive operational saving, and it absolutely justifies building your own infrastructure. Section 2. Words as mathematical coordinates. So if we want to build that highly efficient open-source alternative, we do it by entirely changing the format of the data. We pass our unstructured text, our words and sentences, through a local CPU neural encoder, like a transformer model. This encoder translates those words into dense mathematical coordinates, often represented as a high-dimensional continuous vector made up of, say, 1,536 floating-point numbers. In this multidimensional space, concepts with similar semantic meanings just naturally group together, completely regardless of how they're spelled. Section 3. Measuring semantic similarity. Now that our words are numbers, how do we actually measure the distance between them? To make this tangible, instead of visualizing 1,536 dimensions, which, let's be honest, would totally break our brains, imagine a radically simplified three-dimensional space. In our little universe here, we're measuring just three things: fruitiness on the first axis, sweetness on the second, and crunchiness on the third. Here is exactly how three different items, a fresh red apple, a crisp green pear, and a grilled ribeye steak, would plot out on those three coordinate planes. As you'd expect, the apple and pear score very high in fruitiness, sweetness, and crunchiness. The steak, it scores negatively across the board. And when a user types in a query like sweet, crisp fruit, that query is also converted right into coordinates in that exact same 3D space. To compare our user's query against the database documents, we use a geometric equation called cosine similarity. It measures the cosine of the angle between the two vectors. And what's fantastic about this metric is that it completely ignores the magnitude or the length of the vector. It only cares about the direction. A score of 1.0 means they point in the exact same semantic direction. When we run the numbers, dividing the dot product by the vector magnitudes, our sweet, crisp fruit query and the apple vector result in an incredible 99.1% match. The system mathematically proves they are highly related concepts without relying on matching a single letter. Conversely, if we apply that exact same mathematical equation, comparing our query against the ribeye steak vector, it yields a negative correlation. The database mathematically understands that a steak is basically the complete semantic opposite of a sweet, crisp fruit. Section 4. Navigating high-dimensional space. Now, brute forcing all these float calculations across millions of records is simply way too slow for instant discovery. Vector databases bypass this by building multi-layer proximity graphs, specifically the hierarchical navigable small world, or HNSW graph. Think of it kind of like a highway system. The top layers of the graph act like the interstate, allowing the system to make long-range, logarithmic jumps across the vector space. Once it gets close to the destination, it drops down to the bottom layers, which act like dense local streets for fine-grained neighborhood matching. Section 5. Qdrant's one-bit compression. But we run into a bottleneck. Storing massive continuous floating point arrays in your system's RAM is prohibitively expensive. That's where this number comes in, 96.8%. That is the staggering amount of RAM Qdrant saves by compressing raw, heavy floating point arrays into ultra-lightweight 1-bit binary arrays. So the crucial point is how it actually pulls this off. It achieves this massive reduction through a process called binary quantization. It's an elegantly simple threshold rule. If a floating point coordinate is strictly greater than 0, it becomes a 1. If the coordinate is 0 or negative, it becomes a 0. That's it. Complex decimals become simple on-off switches. Applying this quantization threshold back to our simplified 3D space, the apple and our user's query, which were entirely positive decimals, both compress into an identical binary array of 3 ones. Meanwhile, the steak, which was all negative coordinates, compresses into an array of 3 zeros. We've preserved the semantic grouping, but drastically reduced the data size. Section 6, lightning-fast search execution. Let's dive into the microscopic execution on the CPU. Because we're now using 1-bit arrays instead of complex floats, the CPU can evaluate semantic distance using single-cycle assembly instructions, what's known as SIMD evaluation. It first performs a bitwise XOR operation, followed instantly by a POP-CNT, or population count, to find the Hamming distance. This is incredibly fast hardware-level math. In a single microsecond clock cycle, the CPU runs this operation and sees 0 differing bits for the apple, meaning it's a perfect coarse match, and it sees 3 differing bits for the steak, indicating maximum distance. It instantly separates the highly likely matches from the absolute noise. But Qdrant doesn't throw the exact floats away completely. It balances all of this using a 2-stage execution pipeline. Stage 1 rapidly filters the binary arrays entirely in RAM using those fast SIMD instructions we just discussed. Then, in Stage 2, it only loads the absolute best candidate matches from the NVMe disk to perform that precise floating point cosine similarity scoring we did earlier. So the crucial point you should take away from this is the final result. By marrying the speed of RAM with the precision of disk storage, this pipeline yields a 32 times smaller RAM footprint and an incredible 40 times faster query throughput, all while maintaining over 98% accuracy compared to an uncompressed index. It is truly the ultimate win-win for performance and cost. Which leaves us with this final thought to chew on. Armed with the deep math of vector embeddings and the highly efficient hardware mechanics of tools like Qdrant and Typesense, how will you apply this incredibly powerful open-source architecture to unlock semantic discovery within your own data? The tools to build enterprise-grade search without the enterprise-grade price tag are officially in your hands.